NASA's Parker Solar Probe has come closer to the Sun than any previous spacecraft, and broken speed records while doing so, making it the fastest vehicle ever to travel in space at a blazing 213,000 miles an hour. Parker Solar will execute 24 total flybys of the Sun. Tess is the exoplanet hunter, a NASA MIT-led mission in search of exoplanets orbiting the brightest stars in the sky that launched on a SpaceX Falcon 9 rocket in April of 2018. It now orbits Earth high above the planet, focusing on stars visible from the northern ecliptic hemisphere. Landsat 8, the most advanced Earth selfie stick in the world, was launched in 2013 as a joint mission from NASA and the US Geological Survey. It is the 7th successful satellite in the Landsat family, which has been taking turns recording satellite images of the Earth's surface from low Earth orbit since 1972. The Mars lander InSight is examining the dark interior of the red planet. The lander's title is short for Interior Exploration Using Seismic Investigations, Geodesy, and Heat Transport, which conveniently summarizes its approach to the task and also hints at the logistical complexity of exploring beneath the surface of even our nearest planetary neighbor. The Hubble Space Telescope, a long-term space-based observatory located 340 miles above Earth's surface, launched aboard the Space Shuttle Discovery in 1990 as a collaboration between the European Space Agency and NASA. Hubble's ultra-sensitive cameras and spectrographs point outward toward the universe to collect both the visible light rays that are ordinarily distorted by passing through Earth's atmosphere and a range of other wavelengths that can't be detected from Earth. The twin Voyager 1 and 2 spacecraft has spent the past 4 decades traveling farther from the Earth than any human-made object has ever gone. Though their primary mission was to investigate the rings and moons of Jupiter and Saturn, their trip was extended past these planets in order to get a glimpse of interstellar space.
Thank you. My name is Caleb Sharf. Welcome to this afternoon's program. We are going to spend a little bit of time exploring the universe today. And to help us with that, we have some exceptional astrophysicists, earth scientists, and aerospace engineers. And together with them, we're going to explore part of our solar system. We're going to look at the inner realms towards the outer realms, and then we're going to move beyond. But ultimately, we're going to come back here, back to the Earth. And in all of that, what we're going to learn is about how humanity has extended itself into the universe. Our avatars are out there exploring. Some of those avatars are robots, some of those avatars are telescopes. Altogether, they are eyes in the skies. So without further ado, I'm going to take my seat and I'm going to introduce our wonderful guests this afternoon. And you'll help me welcome them. So our first participant is an astrophysicist and the project scientist for NASA's Parker Solar Probe mission. His research at the Johns Hopkins Applied Physics Laboratory spreads over a wide range of heliophysics areas with an emphasis on the dynamic solar corona. Please welcome Noor Rawafi. Our next panelist is a systems engineer at NASA's Jet Propulsion Laboratory. Her work on the Red Planet includes the InSight Mars lander, as well as its companion mission, the Mars Cube-1 CubeSats. She is part of the team that helped build and test the spacecraft, as well as the operations team. She has also recently joined the Mars 2020 rover team. Please welcome Farah Alibay. Also joining us is one of NASA's exoplanetary leaders. That's an interesting term which didn't exist so very long ago. The project scientist for the Transiting Exoplanet Survey Satellite, otherwise known as Tess, and chief of the Exoplanets and Stellar Astrophysics Laboratory in the Astrophysics Science Division at NASA Goddard. She's been at NASA since 1993, when she was a member of the Hubble Space Telescope instrument team. Please welcome Patty Boyd. And our final panelist, a very special guest, is the director of the Earth Sciences Division at NASA Goddard, and the project scientist on Landsat 8. His career at NASA spans over 40 years, and he now leads a team of over 1,400 scientists dedicated to studying the Earth and saving us all from disaster. Please welcome Jim Irons. Thank you so much for joining us this afternoon. So perhaps to start with, I'm going to cheat a little bit and ask that we have some images from missions that we're not going to talk about directly, but they speak to something I'd like to kick off with. And these are images from the Juno mission to Jupiter and some images from the Cassini mission, which no longer orbit Saturn, but which obtained extraordinary data from that system. And the reason for putting these images up, especially the Juno images from Jupiter, is that they remind me of something that the principal investigator of the Juno mission said. He said recently that people forget that it takes time to get to places in the solar system. It also takes time for a space telescope to be constructed and launched. And in the case of Juno, it was many years after it launched that scientists were essentially sitting around twiddling their thumbs. I'm sure they weren't twiddling their thumbs until it got there. And the interesting thing was, in talking to him about the feeling of when the project that you have been working on sort of reaches its final destination, begins to obtain the information that you have waited for so long. So maybe we could I'll just go down the row here and ask you for any anecdotes from the missions that we're talking about today, the solar probe, for example, for UNOR. Was there a moment in there where you had that feeling of we've arrived, or I'm panicked, or what do we do next, or elation?
Thank you. Parker Solar Probe is a very unique mission. I mean, we've been waiting for 60 years to come to this point. We didn't have the technology to spend the spacecraft so close to the sun and to protect it. So being part of this mission is really a dream come true. As far as anecdotes, Parker Solar Probe, as I said, everything is fast about the mission. Every orbit is about between 3 and 4 months, so everything goes so fast. And we are getting closer and closer to the sun. So every 3 months, we have a period where we are very nervous. But the spacecraft is doing so well, the mission is doing so well so far. So, yeah, wonderful.
Well, I mostly work on Mars missions, so compared to all scientists who work on Jupiter or Saturn missions always say that we have instant gratification because we get to launch to Mars every 26 months or so. That's when the planets align, and it only takes 6 months to get there. But for me, the most terrifying part of going to Mars is the landing. You're probably maybe familiar with what we call the 7 minutes of terror. But basically, when you go to Mars, you hit the atmosphere at hundreds of miles per hour, and you have to slow down your spacecraft to get to the surface, to get down to a few feet per second, right, when you're hitting the surface. And that whole sequence takes 7 minutes. And light takes more than 7 minutes to travel back. So by the time you get the first data, when you're hitting the surface, the atmosphere, you know that your spacecraft is on the surface of Mars, for sure. Whether it's in one piece or many, that you don't know. So I experienced my first Mars landing back in November, and it was both the fastest and the shortest, like the shortest and the longest 7 minutes of my life. I don't believe that I breathed the whole 7 minutes. I know that's not physically possible, but I can assure you. So definitely, when you're seeing years of work, and it all comes down to 7 minutes, you have to sit there and pray it all goes right, and you didn't get a decimal place wrong. Yeah.
Patty, how about you?
I think it's really exciting when you're about to launch a mission, because so much work goes into simulating what you want these instruments to do and this mission to do, and predicting what it will do, and developing to those simulations and predictions. And then you have a whole team of engineers and scientists that have been working on it and getting ready, and as the time ticks down and you're standing there watching or waiting for this to launch, it's a very nerve-wracking experience as well, because there's a lot of years of dreams and aspirations and hopes for the future on the top of this rocket. So everybody is there holding their breath in that same kind of moment, hoping that the launch goes well. And then if it does, then you've got to go through commissioning, which is, now you've got a spacecraft that's in orbit. You need to check it out. You need to get to your final orbital position. And a lot of the planetary missions, and Tess as well, they have to do these close approaches to really heavy bodies. So for Tess, we had to come very close to the moon to get into our final orbit. So everybody's waiting for that to happen and happen successfully. And then when you're finally in your science orbit and you can start to really do science with this spacecraft that you've been designing and dreaming about for years, it's another moment of a bit of terror, because now you're going to get the real thing. You get reality. How does it work? Is it doing what we expected it to? Is the universe going to cooperate so that we can observe what we're hoping to observe? So it's just a very exhilarating experience to go through that year up to launch and then the year after.
And Jim, of course, staring back at the Earth is a non-trivial problem.
Well, we have the shortest trip to get to into orbit for the planet we observe, and launch, of course, is always exciting and tense. In my case, Landsat 8 worked 14 years on it. It's sitting on top of a rocket full of high explosives, and that's always tense. But the point of time when really celebrate is when in Earth science, all of our Earth observation data is available to the public. And when the instruments are calibrated, when the system's fully checked out, when the data are ready to be released, to me, that's a time that has a lot less fanfare, but is equally important to, or actually ultimately more important than the launch. The launch is necessary, of course. And just this week, we launched a satellite called ISAT-2. Its mission is to observe the elevation of sea ice and ice sheets over time. It launched in September. And just this week, the data were released for public availability. So that was a big milestone.
And I must say, it feels like you're walking around, you're having breakfast, you're getting your coffee, you're talking to your neighbors while these things are going on. Does that ever feel extraordinary? Perhaps it does.
Oh,
it doesn't.
Oh, it's absolutely extraordinary. People... It's hard to convey. People don't understand what it takes to develop and launch and operate a satellite system. Just hundreds of people or more working on it, often in partnership with commercial industry or with international partners. And so much is riding on the success of what is essentially a high-risk endeavor that think about it a lot.
When you see a project developing from birth to fruition, it becomes part of you. For Parker, as far as I'm concerned, when we enter each encounter where the spacecraft is really closest to a star ever, I'm wondering every day, I'm praying if everything is okay. I'm waiting for it to go the other side of the sun, tell me I'm okay.
So actually that gives me an excuse to ask you a little bit more about the Parker Solar Probe, and the way we're going to do this is we're sort of moving our way through the solar system as we discuss the science and the missions. And of course, the Parker Solar Probe is a mission to a star. It just happens to be our star. Perhaps you could say a little bit, just for people to understand exactly how close we're getting at our closest approach, and what a few of the primary science goals are.
Yeah, as I said earlier, we've been waiting for 60 years to get a mission like Parker Solar Probe. People thought about a mission like this in 1958, but we couldn't do it because we didn't have the technology to protect the spacecraft. Now we have it, and we launched last year in August 12th. We had 2 encounters with the sun. We are now the closest ever to a star. We are the fastest spacecraft in space. And we'll get even closer. So we will use Venus 7 times. Every time we fly by Venus, we'll get closer to the sun. At the end, after 6 years, actually 5 years from now, because the mission is 1 year old now. So we'll get under 4 million miles from the sun. The Sun-Earth distance is 93 million miles. So if the Earth-Sun distance is one yard, Parker Solar Probe will be this close to the sun. It's almost touching the sun.
It's quite extraordinary. And you mentioned the speed, and this is something that's perhaps counterintuitive for many people. So maybe could you just say something about why is it moving so fast? Don't things have to move fast when they're further out, getting out of the solar system?
Just the gravitational mechanics. When we are close to the sun, the spacecraft would go faster. And for Parker in particular, when we are closest to the sun, the spacecraft will be flying at 120 miles a second. So if you pick a ride on Parker, you can fly from San Francisco to here in about 20 seconds. That's how fast it is.
Okay.
It will make New York to Tokyo in a minute.
That would be nice.
It's nice, absolutely, yeah, definitely.
So let's spend a little more time talking about the inner solar system, and to actually come back to you, Jim, briefly. We mentioned Landsat. Perhaps you could just give us a very brief history of that program, because I'm not sure everybody is aware of what's been happening with Landsat.
Yeah, I hearken back to the 1968 picture of Earthrise from the moon, when many people began to understand the value of observing the Earth from the high vantage point of space. And in 1972, that was the year I graduated high school, so it's an old program. The first Landsat satellite was launched, and with the purpose of repeatedly observing the continental surfaces of the Earth over time. And so now we have a over 40-year record of the Earth's land surfaces, and what it demonstrates is the dramatic changes that are occurring on the surface of the Earth. As our population grows, as our technology advances, we see incredible amount of change and rapid change. Forest disturbance, glacier retreat, the expansion of urban areas, the increased use of irrigation on the Earth in order to feed a growing population. All of these things are visible because we've been monitoring the Earth over this period of time.
And what's so fascinating is at the same time that we've been learning more about our planet than we could perhaps ever learn from being on the surface of the planet, we've also been looking out into the universe. And Paddy, we'll talk more about Tess later, but you were also deeply involved with the Hubble Space Telescope program. Something like a space telescope, just to talk about the technical issues. So it's in a relatively low orbit around the Earth, but there are challenges to that. I mean, you don't want to see the Earth or the Sun. So maybe you could say something about operating a telescope in space and looking at the outer reaches of the cosmos.
It's definitely a challenge. And so the Hubble Space Telescope orbits the Earth in a low Earth orbit. It goes around the Earth once every 90 minutes or so. And it was specially designed to see faintest, furthest objects that we could see. So in order to do that, first of all, you don't want to blow out any of the cameras by looking at the bright Earth or anything bright like the moon, but you also need to be able to point with exquisite precision. So we don't want this telescope to be able to move where it's pointing, even as it's moving around the Earth once every 90 minutes. So there's a lot of equipment on the spacecraft itself to make sure that we can maintain fine pointing like that. There's a team on the ground to make sure that the spacecraft is healthy and doing what we expect it to do by monitoring the telemetry as it comes down. But one of the coolest things about Hubble, it was launched to get above the Earth's atmosphere so that we could see images in the optical with much clearer precision than we could see from Earth because the atmosphere distorts those images, but also it blocks some light that we can't see with our eyes. It blocks the infrared and it blocks the ultraviolet. So Hubble can get up above the Earth's atmosphere, see a much larger range of light, and was also designed to be serviced by astronauts. So there were 5 servicing missions that, as Hubble aged and as our technology got better, it allowed us to go up and make that telescope even stronger, have better instruments on board. And the last servicing mission was just about 10 years ago now, left Hubble at the peak of its capabilities. So it's 29 years and going on orbit, still returning amazing data, doing science that it was never designed to do because the instrumentation and the way that that telescope is operated are just state-of-the-art still today.
And so we've talked a little bit about looking at the sun. We're going to come back to that. We've talked about looking at the Earth. We'll come back to that. And we will move on from some of the discoveries of the Hubble Telescope. But of course, exploring our solar system also means literally going to other places. And so, Farah, maybe I could ask you to tell us a little bit more about the process. And also, actually, I'd really like you to say something about these CubeSats, which I'm not sure so many people realize went along with the InSight mission to Mars.
Yeah, so InSight was designed to look at Mars as a rocky planet. You've probably heard of a lot of the rovers that have gone to Mars that have really looked at habitability and geology and things like that. So InSight is looking more globally at Mars, how it came to be, why it's different from Earth. And so not only are we going to Mars to understand Mars and its interior, it's actually going to tell us more about Earth, because it's going to tell us as to why is it that Mars looks like the way it does and Earth happens to be habitable, because Mars is not fun. It's like minus 100 Fahrenheit at night, right? So when we were landing InSight, there's a number of orbiters actually that are around Mars that were collecting. One of them was collecting the data that was going to come down from InSight during landing. However, because of the way the geometry worked, that orbiter was going to set behind Mars right after the landing, which meant that in the original design for the mission, we were not going to get the landing data in real time. It was going to be about 3 or 4 hours later, which is fine, right? There's nothing we can do in real time to change it, except that if your baby is landing on another planet, 4 hours is really long. So our director, this is right when I started actually, the lab director said, well, you guys are a bunch of smart engineers. Figure it out. Get me that data in real time. And it was literally a couple of engineers back of a cocktail napkin that came up with the concept of flying CubeSats. So CubeSats are small spacecraft that have been developed for university purposes, actually more for learning purposes. They're literally the size of a sort of a wholesale cereal box, so not too big. It's 30 by 20 by 10 centimeters, so about a foot long. And so we came up with a crazy idea of like, well, there's these CubeSats these universities use. Let's just send one to Mars. And no one had ever done that before. We only sent them around Earth orbit. And so we sent
You told someone you were doing it, so you didn't just sneak it in.
No, we had to tell someone. We actually literally strapped it up on the back on the rocket. It was not even in the fairing with the spacecraft, because the InSight mission was like, no, you're not coming with us. Like, no way. This is some science experiment, and it's going to go wrong. So we literally strapped it on the side of the rocket. And yeah, there's these small CubeSats that made their own way to Mars with the little set of thrusters. That the fuel that we use is actually from the same thing as you have in your fire extinguisher, and that is what we used to get to Mars. And successfully were able to get that landing data on landing day from those tiny spacecraft.
Interesting, and I think also, as you're talking, these issues of the sheer effort required to go somewhere and the things you have to do to protect and monitor your baby, right? And I think, to come back to you, Noor, the Parker Solar Probe is experiencing a pretty extreme environment when it gets close to the sun. So much like with Farah and all of you, you want to protect your baby. And so perhaps you could just say a little bit about the design of the Parker Probe that allows it to withstand. What kind of temperatures does it experience?
Okay, let me start off saying a star is a different animal. It's not a planet. It's not a moon. if you take the example of the sun, by itself, it weighs 99.98% of the total mass of the solar system. The sun is huge, and it's so active, it has a strong magnetic field, it can harm you at any moment. So if you have your spacecraft there and you don't protect it carefully, it can be gone in no time at all. So for Parker, for example, one huge challenge was the environment, the heat that we're getting from the sun. The thermal protection system that has to face the sun at all time, the side that is facing the sun will be subject to temperature in excess of 2,500 degrees Fahrenheit. The spacecraft itself has to operate at room temperature. And the TPS is not, it's 2.3 meter wide, and it's 4.5 inch thick. It's not big, it's not even very heavy. Betsy will tell us more about it later. And more than that, it's not only the TPS. There is the pointing of the spacecraft. It has, as I said, it has to face the sun at all time. Of course, it can wiggle a little bit here and there, but you know by how much? It shouldn't exceed 1 degree.
So there's no peaking.
Exactly.
Otherwise, you get
1 degree.
to a crisp.
And the nice thing about it also, when we are closest to the sun, the spacecraft has to be 100% autonomous. If something happened to it, it has to solve it by itself. We cannot do anything for it. That's how challenging to get so close to a star.
So I believe we actually have a tech demo for everyone. So we have a demo that involves fire, and it also involves some of the material that is currently on the Parker Solar Probe. So we'd like to welcome our next participant from the Johns Hopkins Applied Physics Lab. She's the lead engineer on the heat shield that protects the Parker Solar Probe from the sun. She's going to show us just how that heat shield for Parker Solar works. So let's please welcome Betsy Congdon.
So Noor gave a very nice introduction to this heat shield. And this is, what I'm showing right now, is actually a sample from the heat shield. Same 4.5 inches that Noor mentioned. I'm going to get the front surface here not quite to the 2,500 that he was talking about, but we'll get it glowing hot. I can certainly feel the heat here. Noor mentioned that we're going really fast, and one of the challenges when you're going really fast is you still have to get out of Earth, and so we had to be very lightweight. So the heat shield's very big, as he mentioned. It's very thin, and that 8-foot diameter frisbee, as we like to call it, because it's basically a really thin shield, is actually only about 150 pounds, ultimately. And the way we do that is we have this sandwich panel, as you can see. Both sides, I can't touch the front right now because it's getting pretty hot. Both sides are a very thin composite, a lot like what you'd get in your golf clubs or in your tennis racket. It's a carbon-carbon composite. We're starting to get the front side here glowing red, as you can kind of see. And so it's a couple hundred degrees. I'm certainly feeling the heat standing here. Maybe, and cannot touch the front. And then in between the two very thin face sheets is a carbon foam. And that's all together in a sandwich panel, which is how airplanes are made, but just not at the same kind of high temperature materials, but very similar engineering construction. So you can see I got it glowing red hot there. It's pretty hot, I can't touch that. I'm gonna turn this off a second and show you that the backside, touch with my hand. Can't touch the front.
She is touching it.
So it's very thin. Can't get too much closer than this. It's pretty hot. But back here, it's nice. And the spacecraft, just like the spacecraft, it's room temperature.
Thank you. Noor, while they're putting that away, so is that material fragile? I mean, it's obviously extraordinary at insulating. But is it a fragile shield in front of the spacecraft? Is it?
It is.
Yes.
It is. It's not, if you hit it by something, it will just shatter.
Wow.
Yeah. Before launch, we had so many concerns about the TPS and other things, but the TPS in particular, because I said it's a big structure, it's not very thick, and Betsy, I don't know if you mentioned it or not. Most of the foam between the two-faced sheets, it's basically like vacuum. It's like a sponge. So just from the vibration from the launcher, that can cause harm to it. But it made it to space. Things were fine. It's in one piece. So
Well done.
absolutely. and just to add, before NASA selected Parker Solar Probe, it commissioned EPL to look into material that can protect the spacecraft years ahead of time. That's how important this piece of technology is.
And I think that's an interesting point. So much is developed years and years ahead. Pieces are put together and ideas are tested and tried and so on. So we're going to move on to sort of our second act now. We've in a sense, been talking about stellar space. Now we're going to move on to talk about interstellar space and beyond, before eventually coming back to the Earth. And I think it's hard to talk about interstellar space and leaving our solar system without referring to the famous Voyager probes, which I'm sure many of you have heard about and are familiar with. And as you may know, a few years ago, we got evidence from the Voyager 1 probe that suggests it has, in some sense, begun to leave our solar system, entering into what's called the interstellar medium, so the gas and particles between the stars, so almost getting outside of the direct influence of the solar atmosphere, which is extending far out into our solar system. Maybe I could just throw this out to whoever wants to respond to it. What did that feel like as a scientist, as an engineer, to know that something humans had constructed was essentially on its way to the stars? Does anyone want to share their reaction to that?
Inspirational. I mean, it's really, even though I'm an earth scientist, I am.
I wouldn't say even.
Well, okay. It's inspirational to realize that we are able to send man-made satellites. Well, they're not satellites; they're spacecraft beyond the solar system and begin to sense the environment outside of our solar system.
I think what's amazing about Voyager is that we're still getting data back from these spacecraft. You know, they were launched in 1977. They have 1977 technology on them at best, but they're still sending information back about once a day, and they're probing a part of our solar system that we have no hope of reaching in our lifetime with our own eyes and our own hands. So it just blows my mind that we're able to get information back from a probe that's that far away.
It's pretty incredible. The building behind my office at JPL is the heart of, we called it the center of the universe, because it's where the Deep Space Network, which is our network of antennas on Earth that listen to every single spacecraft out there in the solar system and beyond. All that data is collected in that building, so you can actually go in and see the data coming down. So every day, I walk out there fairly often, and you can see the Voyager 2 data coming down to Earth, and it's a trickle of data. And it was never designed to send data out that far out. In fact, so much that when you get data from Voyager 2, the data that you're getting is not above the noise level. So you get noise, and if you're ever in your radio, if you're listening to the radio and you're too far away from the station, you start getting white noise, and you can barely hear the music or whatever behind it. Well, that's basically what listening to Voyager 2 sounds like. So we actually have the spacecraft repeat its message multiple times, and then we can take out the noise and listen to Voyager. But it kind of brings it literally back down to Earth when you see that data coming, and you're like, this is coming all the way from beyond where we'll send people, right?
You have to give credit to the engineers who build these devices, and they can last for decades and decades. If you look at any mission, usually they are designed for a very limited period of time, but we end up extending them by decades. And in the example of Voyagers in particular, the computers on board are way less performant than the simplest calculators we have on Earth here. And they are still working after 40 years. That's amazing.
Am I right in thinking there was actually tape?
Yes.
Yeah.
Yes.
Magnetic recording tape
Yes.
on the Voyagers?
Yeah. Yeah.
Extraordinary.
It's amazing.
Yeah.
It's really amazing.
And this is an opportunity also to bring up something which I think is very interesting, is relating the history of something like the Voyager mission, which started in the 1970s, to what else has happened in science since it left. So specifically, relevant to this panel, is the discovery that there are other places out there around other stars. There are planets around other stars. So Paddy, perhaps you could talk a little bit about that. Just what has happened? So Voyager launched in
1977.
1977. We didn't know that there were other solar systems out there.
We hoped, we dreamed, when we didn't think we had a chance of ever observing evidence of a planet around another star at that time, because stars are big and bright. Planets are small. They don't give off their own light. In the case of the sun and the Earth, the sun is 10 billion times brighter than the light you would see reflected from Earth if you were observing. So it seemed like an impossible problem, but we really wish there were planets. We had science fiction all about planets around other stars. So when the Voyager probes were going out and taking these beautiful kind of game-changing images of Jupiter, Saturn, and then Uranus and Neptune, these were still the only planets that we knew about in the whole universe. And then slowly, our technology got better, our methods got better. We stopped thinking about our solar system as the only kind of solar system that you could have. And when all those things started to combine, planets started to come out of the data. Just like faint calls, like we were just talking about the Voyager signal, teasing out a signal from the noise is very tricky. And if you're only looking for something that looks like our solar system, you could miss it. And that's exactly what was happening. That the first planets that were discovered in the mid-90s, the very first planets that we could confirm, just like 1995, were planets that look nothing like the planets in our solar system. They were bigger than Jupiter, which is the biggest planet by far in our solar system. And compared to Jupiter, which is way out beyond Earth, these Jupiters were so close to their star, much, much closer than Mercury, that their orbits were just on days periods. So that was a huge change in the way we thought of our observable universe when we could finally detect planets around other stars. And then once those first discoveries came in, you saw the floodgates open. Everybody came up with new methods of detecting them. We knew that there were all kinds of planets around, not just like the ones in our solar system, and it's just been a really exciting ride for about the last generation. As you see, we go from just a few planets around other stars that we know about to now about 4,000 confirmed planets around other stars, and the ability to say, because of that statistically, that there are actually more planets than stars in the galaxy. So more than 100 billion planets. It's a big change from 1977.
It is, and perhaps this would be an opportunity just to talk a little bit about the Tess mission, which is relatively newly launched and operational. And maybe you could just tell us about what Tess's place is in the science of exoplanets and its strategy, and what is it doing right now?
So if you have an answer now that you haven't had before, and the answer is that planets are everywhere and all kind of planets populate our galaxy, then the next logical step is to find our nearest neighbors. So Tess is designed to take that next step. Tess is actually a fairly small astrophysics observatory. It's only about the size of a washing machine compared to Hubble, which is like a school bus. And it is in a really interesting orbit around the Earth. It orbits on an elliptical orbit. It's mostly out there going slowly on this elliptical orbit. But every 2 weeks it comes close to Earth and it dumps a whole bunch of data all at once from what we call an observing segment. It looks like an orange slice. So each one of those segments you see up there is an observing sector, and we stare at that region without blinking for 27 days straight, 2 orbits. And what we're looking for is a tiny dimming in the star's light as a planet passes in front of that star. So did anybody have the good fortune of seeing the transit of Venus in 2012? This is when Venus passed in front of the sun. Some people did see it. You saw the amazing little Earth-like planet passing in front of our star, the sun. That's exactly the method that we're using. Kepler used it before, and Tess is using it now. We monitor hundreds of thousands of stars all at once, waiting for that tiny little dip, which is called a transit, to pass in front of the star. We see the dip in our data, and we can learn a lot from that dip. We can learn about the size of the planet with respect to the star because it's covering up an area of the star that is directly proportional to the dip. And we can measure the period of the planet because the dip is repeatable. So once we've measured the period, we know where that planet is with respect to the star. That means we can say how close to the star it is, how much energy it's getting. Is it in what we call the habitable zone, which is where liquid water could pool on the surface? Tess is actually going to find a lot of planets that are much, much closer to the star than the habitable zone, much, much closer than even Mercury or Venus. But we're taking the census of our nearest neighbors. We're about halfway through the survey. We're in sector 12, it's 13 in the southern hemisphere, and then we'll flip around, do the exact same thing in the northern hemisphere, and we're predicting that we will find thousands of exoplanets around some of the nearest and brightest stars.
And of course, the Hubble Telescope has also played a role in the study of exoplanets, not necessarily so much in terms of discovery, but in terms of that follow-up, kind of following up the sorts of things that Tess is going to find, and obviously subsequent telescopes after Hubble are going to perform some of that. So this gets me to another aspect of our exploration beyond our solar system, which actually is Hubble. It's been around a long time. Maybe could you just remind us, how old is the Hubble Telescope?
In April of this year, it turned 29 years old. So next year, it'll be 30 years in space, operating that entire time. That is unprecedented for astrophysics missions. And still doing amazing things because it's an amazing observatory with really exquisite instrumentation on board. And so it can make measurements that scientists think of great measurements to make. Hubble can make them within reason. And so it was launched before exoplanets were even discovered. It was launched in 1990. We didn't even know about the first exoplanets until 1995. What you can do with the instrumentation on Hubble, though, is that you can design innovative observing programs so that you can look at some of these star systems where we know there are planets, and you can take a spectrum of the light of the star as that planet passes in front of the star and compare it to the spectrum when the planet isn't there. Looking at the difference there, you can actually see how the atmosphere of the planet, if it has an atmosphere, is interacting with the sun's light as it transmits through the atmosphere. So we're already beginning to put together some of the fingerprints of some atmospheres around planets using Hubble, looking for things like water vapor and sometimes other chemicals in the atmosphere that can tell us what's going on in these places.
And I don't know if we have the images, but Hubble has also played a pivotal role in observing the birthplace of stars and planets. Maybe could you tell us a little bit about the image we're seeing?
Right, and so that's a really good example of how science is always kind of moving forward and not always in lockstep, but as a group of different disciplines. So we didn't know very much about how solar systems formed. 1977 when Voyager launched, and we kept putting more information on that. We were assuming that our solar system formed from as our star was collapsing, there would be a nebula around it that could form planets. With Hubble, we can actually see these birthplaces of stars. So this is one of the most iconic images from Hubble. It's called the Pillars of Creation. It's actually a very small region of a much larger young star-forming region. And what we're seeing there are some of the brightest, biggest stars, really young stars that have tremendous winds that are blowing material away. They're evacuating some cavities there. At the tips here, you can actually see stars we think are still just being born, very, very young protostars. And as they turn on, they start to sculpt out some of that gas and dust. So it's almost like sandstorms are sculpting out the sand on the Earth. These storms of star birth start to sculpt out the gas and the dust and make these beautiful structures. This is about the visible range of the spectrum. We combine different filters in Hubble to tell us where the different elements are, and different regions are colored differently, and then you can combine that into a full color image. So this is really what we would see if we could play around with our eyes in Photoshop, but still only mostly in the visible spectrum here. We didn't really know what was going on in there until we could use an infrared camera on Hubble.
And this is the infrared.
Oh, then that's the same region. with the infrared camera on Hubble. So that's one of the newer cameras that was placed on the spacecraft. And what you can see is that we're peering beyond the veil here. The earlier image, you could only see the brightest stars. Now you see dozens and dozens of young stars. And so that's because the starlight is passing through the gas at infrared wavelengths, allowing us to peek into these stellar nurseries. And it's one of the things we look forward to the most with the yet-to-be-launched James Webb Space Telescope, which will launch in 2021. It's going to take us even further into the infrared to allow us to see even further through these beautiful gas and dust clouds.
And I think there's a beautiful symmetry between visiting our own star and observing the birthplaces of stars elsewhere in the universe. I mean, that is an extraordinary time in human history where we can do that, where we can look at one star up close, well, not too close, but close enough, and then see these other stars forming, potentially planetary systems forming around them, and then, of course, we can detect planetary systems themselves. I guess I'd like to talk a little bit about, what happens next. So we know the Voyager probes will continue moving onwards out into the galaxy, albeit at a comparatively slow pace. Just to finish with Hubble, what's going to happen to it in upcoming years? Do we know how long it will remain operational in orbit?
So we don't know, but we can certainly make estimates based on all the data that we get from the instruments, the critical systems on the telescope. And we have a team of scientists and engineers working together on the ground to extend the lifetime of Hubble as long as possible. And so we are now very focused on keeping Hubble operational till about 2025. So we would really like to have some overlap with James Webb and Hubble because they're super powerful and the fields of view on both of them are very, very narrow. So even though Hubble has been operating for 30 years, it only looks at these tiny little dots on the sky every time it does an observation. It hasn't seen nearly everything, not even close. So we're very hopeful that the systems can remain healthy. There are things on board the spacecraft that might break before any of the instruments do, like our ability to do some fine pointing. But in that case, we also have backup plans. So if you couldn't do the finest pointing, you might lose some science, but you might gain other scientific programs. We actually get 10 times as many proposals from the community as we can ever do in 1 year. So there's a huge amount of good science you could do with Hubble, even if it was slightly degraded. But everything looks great now. We are very, very hopeful that we're going to make it into the mid-2020s with Hubble operational, and we can't wait to see what that looks like.
And just to wrap up some of the technical issues, Farah, you talked about the Deep Space Network, and I think for many of us, if we hear Deep Space Network, it evokes all sorts of images, but it's a central piece of linking together so many of our scientific instruments and our exploration vehicles. Perhaps you could just very briefly tell us, so what is this Deep Space Network physically? I mean, is it some solar system web out there?
It's on Earth. It has a cool name, but it's basically just a set of antennas. So it's a set of really big antennas, right? The bigger ones are 70 meters, the smaller ones are 34 meters. And they're set in 3 different places around the Earth. So we have them in Goldstone, California, in Madrid in Spain, and then in Canberra in Australia. And the idea, right, is that you have northern and southern hemisphere and kind of spread out around the world so that at any given time, these antennas can look out and at the universe, essentially. So from any point or any time of day, we can see, quote unquote, all of our spacecraft. But all it is that big radio antennas. So when our spacecraft, when our babies call home, we're always there to listen. We just need big antennas because they're further, the spacecraft are further away.
And so, since we've talked about aging spacecraft, aging missions, communication, and the like, it's almost time for us to sort of turn back towards the Earth in our program this afternoon. And I think we have a short video to show, which just reminds us that when we put things into space, we tend to make a bit of a mess, and that some of these old things stick around for a while. So I don't know if that video can be queued up.
Space junk is what's left over from when we launch things in space, or it's either generated by inappropriate behavior, essentially. For example, when something is launched into space, there's always shrouds, there's things that hold various stages together, and those things are released, and that becomes part of the space junk. But the more important sources of space junk is, for a long time, there were satellites exploding in Earth orbit, and no one even knew that that was going on because no one was charged with keeping track of where the stuff was coming from that was causing all of the debris. There's this collisional cascading phenomena that you have very little control over, and when things collide with one another, they create not only a large number of trackable debris, but an even larger number of smaller debris that can damage spacecraft to the point that you create an environment that exceeds the hazard from the natural meteoroid environment. This cascading phenomena has the characteristic that the more collisions that take place, the more probability there's going to be future collisions. Right now, we're at the point that about every 10 years you'd expect a collision between two large objects, and a shorter period of time between a large object and smaller objects. It's been stated that if there were a war to break out between two countries, the first thing you would want to do is to wipe out the satellites, because they are the communication tool that people use, and the observations. It's their most vulnerable part of any conflict. That's true of the military, but it's also very true of even the civilian community. We're starting to depend on those kind of things for communication. All the models right now are saying that we have reached a point in low Earth orbit where even if we quit launching things into Earth orbit, there's enough debris already up there that this cascading will continue to grow, and it won't quit until you've turned everything into dust, and then it can start re-entering. But that's thousands of years in the future.
So I don't want to have that sound too awful a note on everything, but clearly it comes back to now we've talked a little bit about looking far beyond our own solar system, interstellar space and so on, but now turning our focus back towards the solar system. I mean, in very practical terms, this is challenging. I mean, this is certainly for Earth orbiting vehicles. I mean, Jim.
So our satellites are tracked, and events occur that are called conjunctions, which means two objects in space are getting too close to each other for comfort. And when that occurs, we use thrusters on the satellites to adjust the orbits to ensure that the distance between the objects are at a safe distance. So, and those are for the satellites where we have control, and we're not. So they have to avoid objects that are no longer controlled in space. And it's a daily, hour by hour, minute by minute monitoring of the space environment.
I mean, Mars has a few things orbiting it, but it doesn't really have space junk yet, right?
No, we don't go to Mars as often. So, we have a few orbiters around Mars, and obviously we've had a few spacecraft land on Mars. When we land on Mars, for example, we do have a back shell and a parachute that, or in the case of Curiosity, we even had a whole descent stage. And that sort of just crash on Mars, and people do get upset about it. They're like, "You're littering Mars," and I'm like, "We only go there like 3 times a decade. I think it's okay." But it's true. There's little pieces of leftover spacecraft. I'm sure the Martians are not happy about it. That in their backyard.
Maybe they're very happy. This is,
I mean, they can go mine, and they're like, "What is this metal?" We don't quite have to worry about it yet. But certainly, it's something that we monitor. We know where these things are. Because, for example, if we're to send more rovers or humans there eventually, we definitely want to make sure that this isn't in their way. And we also have to make sure that it's very clean, because we don't want to bring, there's something called planetary protection. We don't want to bring bacteria from Earth to Mars. It's a little bit, I'm sure many of you are familiar with Star Trek, but one of our missions at NASA, right, is that we observe peacefully. And we are not there to take over Mars. We're just there to observe and learn. So as part of that actually means that we can't infect Mars with whatever is coming from Earth, because we're not sure, actually. There could be bacteria from Earth that could survive on Mars. It's not our job to go invade Mars. So there's definitely, we have to make sure our junk is clean, basically, so that we don't go spread all sorts of disease over there.
and I can't resist bringing this up, obviously we've heard a lot in recent weeks about certain billionaires discussing not just expanding human presence in the solar system, Jeff Bezos, but also Elon Musk talking about going and colonizing Mars. He wants to put 10,000 people on Mars. People are filthy, right? I mean, is there, this is a general question for anyone who knows the answer, is there discussion between the science community and people who are making these grandiose plans for us as a species?
I actually don't know. I work with robots, so I don't know. Robots are easy. They don't breathe, they don't have feelings. It's great.
Right.
I would guess neither one of them is going to get to Mars alone, right? It's going to have to be a commercial government partnership, at least at this point in time. But I think it's really interesting that we're having these conversations now. Yep. And so I don't think that we will be colonizing Mars anytime soon. It is a very, very hard problem. But we do have an island nearby that we can experiment on, so we can figure out how we would do it on the moon. And you see NASA and commercial organizations talking a lot more about that in a more a real, deliberate way these days. So I'm not sure how Jeff Bezos and the like will work it out with NASA in the future for Mars, but I think we have a great platform waiting for us on the moon to try it out.
So perhaps that's a good moment to come to our third and final act in the program today, which is to come back to the Earth and think about what we've learnt about our home world. And in a sense, so much of what all of you do is about finding context. I mean, Jim, obviously, you're more directly involved in studying the Earth, but finding exoplanets, exploring Mars, understanding our star are all centrally important to placing ourselves in proper context, not just in a philosophical sense, but really understanding the nature of the Earth system. And so, Nora, just briefly to come back to, learning about our sun is not just about doing heliophysics. I know heliophysics is wonderful, but some element of that mission is about learning more about how our star influences the Earth. Is that correct?
Exactly. We basically live in the extended atmosphere of the sun, that is the corona. The corona evolves to become the solar wind, and the solar wind is blowing all the time past Earth. And as I said earlier, the sun is so huge. Whatever happens on the sun will affect us in one way or another. Imagine, for instance, you have one of these big flares or CMEs that erupts on the sun, and it's hurtling toward us. In the best case scenario, we will have some aurorae on the poles, and we can enjoy them. In the worst case scenario, we'll have a lot of damage to the space equipment, GPS, telecommunication, and everything. And if these events are strong enough, they can shut down the power grid. And imagine if that happens for an extended period of time in cities like New York or San Francisco or whatever. I mean, Wall Street will shut down for a month, and we will have losses by the trillions, meaning that the economic system will collapse. And if that happens, social unrest will erupt almost everywhere. And if, God forbid, that happens, we basically lose all the knowledge that we gained so far, and we are basically thrown back to the Stone Age. So it's really important that we understand how the solar corona works. And that's exactly why we are sending Parker Solar Probe there. Let me add just one thing just to connect to exoplanets. Parker Solar Probe is our ambassador to extend our knowledge of how stellar winds works in general. We can observe the sun and the solar corona in a lot of details. And the knowledge we gain there, we can just apply it to the small planet. Well, they are not small, but the distant planets, and they are affected by stellar winds in similar ways like we are affected by the solar wind. So Parker Solar Probe is our ambassador. It's our window toward other venues in the universe.
And that reminds me, I think we haven't experienced a truly enormous solar event here on Earth for a long time. I mean, there was a famous event called the Carrington event, I think.
That's I think, the strongest event in recorded history. It occurred in 1859, and it was actually witnessed by an amateur astronomer, Richard Carrington. That event happened on the sun, and 2 days after, we get the strongest geomagnetic storm on Earth. It was so huge that nobody could believe what they were seeing.
I mean, I understand the telegraph poles were catching on fire
exactly.
because of the electrical currents
Yes.
induced by this.
So that if one event like that happened now, the power grid will be gone. And statistics tells us that this type of events happen once every 100 years. So we are basically overdue for one of these big events. We have to watch.
So let's let's talk a bit about Earth.
Yes.
Let's come to Earth. I mean, so all of these things feed into our understanding of the planet. And Jim, I know we have a few illustrative animations and videos to talk about. I think data from Landsat, one of the Landsat missions.
Yes.
Maybe you could, if we can get those up, talk us through some of that, and talk us through, what do we gain by having eyes in the sky that look back at our home planet, and how do we do that?
Well, this first animation illustrates how we are able to observe the entire surface of the Earth from space. This is a animation of Landsat 8, which is flown in a polar orbit. During the sunlit portion of the orbit, it flies from north to south and then goes up the other side of the Earth from south to north. As it's going over, it's imaging a swath of the Earth's surface, about 100 miles wide on each orbit, about 14 to 15 orbits in a 24-hour period. And the Earth is rotating below the orbital plane of the satellite. So every orbit, it sees a different swath of the Earth. And then over a 16-day period, the entire surface of the Earth comes within view of the spacecraft, and the orbit is maintained so that on day 17, it starts all over again, and it starts on that first orbit, and that enables us to get that repetitive view of the Earth's surface on a 16-day cycle. And the purpose is to observe intra-annual changes, that is seasonal within the year, how the Earth is changing, how the men and women are impacting the surface of the Earth, and then we do it year after year so we can understand inter-annual changes, observe how the Earth is changing over multi-decadal periods. This is, for example, a time series of Landsat images of Shanghai in China. I think the years are over on your left-hand corner, and what it's demonstrating is a phenomena that's shown all over the Earth. Most of our urban areas are growing, and the reason is, first, our population is increasing, and second, the proportion of our population that is living within urban areas are increasing. So this is putting a great deal of pressure on our urban infrastructure. As if you're in New York City, I think you can appreciate that. So that's one example. This next animation shows glaciers in Glacial National Park. When Glacier became a national park in 1910, there were about 150 glaciers throughout the park. There are now fewer than 25. And those 25 glaciers are retreating every year, about 2 to 3 acres per year for the Grinnell Glacier there that's at the top of the image. So we can see those changes and the impacts of climate change on glaciers. This is a time series of images over the U.S. showing our forested areas. Healthy forest is in green, and forest disturbance is shown as yellow. This is Broken Bow Lake in Oklahoma, which is a state park, and there's an area protected. But all around it, timber harvesting is occurring. So you see that annual impact of land management on our forested lands, and this impacts how much carbon is stored from the atmosphere every year. So we can move on to, this is West Virginia, Boone County, West Virginia. Another form of forest disturbance is mountaintop removal for coal mining. And it can disturb, fairly substantial acres of land. We'll move on here, I think, to other examples of forest disturbance. But the point is that we can, every year, monitor forest disturbance as it's occurring, and then make calculations to determine how much carbon is assimilated from the atmosphere and the impacts of forest disturbance on that quantity.
So let me ask you as well. I mean, you've spent many years in a very privileged position of peering down at the Earth with some of the highest fidelity scientific data we have of our home planet. Other things that have particularly surprised you, not necessarily negative things, possibly positive things that you're seeing happening to this?
Yeah, there's some good news. First of all, when I first started looking at Landsat imagery, what struck me was the aesthetic beauty of the Earth, and these images are from a collection called Earth is Art. And just observing the geomorphology of the Earth from space was stunning. But now, as I've gone through my career, what is even more stunning is the impact of our human activities on our observations of the Earth. And so I like to use the word privilege. That it has been a privilege to observe things. Not all bad news. Some of our other observations from space have shown, for example, that air quality has improved across the nation and globally. We're also able to observe from space the impact of the Montreal Protocol, which regulated and basically banned the production of chlorofluorocarbons. And we are able to track the ozone hole, that is the concentration of ozone in the stratosphere, the upper layer of our Earth's atmosphere, and the ozone, the degradation of the ozone hole has slowed or ended, and hopefully in the near future we'll see those ozone concentrations increase. And it's important because the ozone in the stratosphere protects us from the ultraviolet radiation from the sun, and allows us to walk out into the sun without burning and exposing ourselves to the threat of skin cancer, for example.
And perhaps I just throw this open to all of you. Other than Jim, you guys don't necessarily spend your time looking back at the Earth, but obviously you're familiar with the science. When you see these images, does it prompt any thoughts in you? Does it help confirm your enthusiasm for the science you do participate in? Do you see the link between this and what you're doing, Patty?
So I think, one of the things that drives exoplanet science is to find a habitable world, right? And our only example is the one we're all on right now. It's the only habitable world out there yet where we have definitive proof that life started and is flourishing. And we know from, Earth scientists that do records going back that the Earth has been very dynamic, actually, but on a slower timescale, and that the atmosphere itself has changed, and some of those changes have allowed us to flourish the way that we have. Others have sometimes been catastrophic to life on Earth. So when I look at what I'm seeing here, I think about this beautiful habitable planet that we live on, and I'm seeing the changes happening so rapidly, just hoping that we can keep it all in the very delicate balance that looks to be so special. When we look out beyond the Earth, we've got Mars and Venus pretty close by. They're kind of small. They're like habitable-sized planets. They're kind of close to a habitable zone. They're around the same star that we are. But you would not want to try to live on either one of those planets. So just feel like we need to preserve our little planet here and keep thinking about what a habitable planet will look like elsewhere.
Yeah, a lot of the work that I do, looking at the solar system and Mars in particular, everything stems from our desire to know more about ourselves, right? Two of the big goal that NASA has for robotic exploration right now is to find possible life within the solar system. So we look at icy moons and that may have life. But for example, even with InSight, we're learning about the interior of Mars, but more specifically how Mars was formed. And all of that is because we ask ourselves the question, why are we here? Who are we? How did we come to be? Which basically comes back to looking at Earth and ourselves, right? So for example, what InSight is doing is it's trying to find out, well, again, right, Earth and Mars look very much alike in terms of if you were just seeing two planets, but Mars evolved a very different way. It became a single plate planet. It has a giant volcano on it that is now extinct, but it's bigger than Mount Everest. It has these really deep canyon that, if it was on Earth, would run from New York to LA. But it's a third of the size of the Earth. It no longer has a magnetic field. It's lost its atmosphere. Something happened to Mars, and we're asking these questions not just because we're curious about Mars, but mostly because we want to understand our planet and our future better. So yeah, although not all of us look at Earth on a day-to-day basis, I think the big picture is always about understanding ourselves. That's always been what exploration's been about.
Nora, do you have anything to add?
Exploring space is fascinating. Exploring Earth is also very fascinating. There are places on Earth that we never set foot on. Take, for example, the deep oceans. There are creatures there. When you see them, they are just amazing. And as you all said, I think it's really important that we preserve that. Let me go back to the sun. When I mentioned early solar activity, I mentioned it in a way that may give it a connotation that's bad. Actually, solar activity is necessary for us to develop Earth to develop life on Earth here. There are studies out there suggesting, and they think they are right, that without solar activity, without solar wind, Earth would not have existed on Earth. Life would not have existed on Earth. So there is a balance to everything. Solar activity is good, it has bad sides. Our activities here on the ground, they are good, but they can also have bad sides, and we have to keep that balance all the time.
Well, I think we're actually at a point where we might switch to taking some questions from the audience, but I'd first like to just thank our panelists. And we have time for a few questions. In the front row here, there's a microphone coming around. If you would wait for that. Here it comes. Thank you.
Thank you. Dr. Noor, I'd like to understand something. When the Parker probe comes close to the sun, you've explained how it deflects the heat, which is incredible. But how does the Parker probe then transmit signals back to the Earth, given the bath of radiation? How is it possible to have a transmitter that powerful to convey images or sensor data? And what is the sensor data that is being retransmitted back to the Earth?
Excellent question. First of all, when we are closest to the sun during the encounters, we don't communicate much with the spacecraft. We have only what we call beacon tones. These are very small pieces of telemetry that tells us basically the overall state of the spacecraft, whether it is in a good shape or in a less good shape. But so far, everything is fine. We have to get far away from the sun, and with the geometry with Earth has to be right, that the antenna of the spacecraft can see Earth. And that way we can communicate with the spacecraft. We can upload stuff, we can send stuff to the spacecraft, and the spacecraft can send data back to us. It has to do a lot with geometry. For example, when the TPS is blocking us, we cannot see the antenna, we cannot communicate with the spacecraft. And we have periods like that. There are, usually we have the encounters where we cannot communicate with the spacecraft. These are 11 days long, but there are certain orbits that are so bad, the geometry is not good, and we cannot hear from the spacecraft up to almost 50 days. And during all that time, It has to survive by itself.
So this is where you feel for your baby.
Yes, definitely. These are critical times, yes, definitely.
Over here on the end.
Thank you. Fascinating session, and thank you for all the tremendous work you all are doing and the advances you're making. So it was intriguing to hear about how much broader our neighborhood is with billions of planets and stars and the broader universe. Could you comment a bit about what we know today with all the advances that you all are making and your counterparts about life beyond the Earth?
So all we really know is what we can see here on Earth. But we know that life did start on Earth and flourish. So if we're going to try to look for other places where life might be, we should look for conditions that are similar to what we believe is absolutely essential for life on Earth, and that is liquid water. So we have not yet put any kind of a definitive data point on whether life exists beyond the Earth. But we keep trying, and we're getting better and better and more sophisticated with where we would look and how we would look all the time. So there are some places in the solar system that are very intriguing to look for signs of life, not just on Mars, but on some of the icy moons around Jupiter and Saturn. We're learning more and more about the water budget on those planets with time, and that's really exciting. But we're also figuring out ways that we could interrogate the atmospheres of some planets to look for what we would call biosignatures. So when you look at the spectrum of an atmosphere of a planet, it's going to have all kinds of chemistry going on in it. But some of it's not going to be in what we would call like an equilibrium situation that would be a natural condition. Some forms of like oxygen and methane, they work together when there's a living biosphere on a planet to put those in disequilibrium. And if we could now come up with a really good instrument and telescope to try to measure those in disequilibrium, we'd have it one more step about whether or not that could possibly be a biosphere. So NASA's actually designing the future missions right now. We're about to take a step back and figure out what type of mission would come after the James Webb Space Telescope and the Wide Field Infrared Survey Telescope. And there are 4 different architectures at the table, and at least 3 of them are designing their instrument parameters around whether or not they have enough signal to be able to do these spectral signatures of other atmospheres. The other one is an X-ray telescope. They're not going to be looking for that particular signature. So I think we really want to get there. We want to have that first piece of information that tells us that life is not just unique to the Earth, but perhaps ubiquitous in the universe, or maybe very rare in the universe. But we're getting closer all the time, and I think it's a really exciting time to see all these things coming together, where we could look and how we could look better. So I'm pretty hopeful that in my lifetime, we'll have some much more definitive information about that question.
Hi. This is a question mainly for Jim, but for anyone. So the work that you do is obviously extremely important for us to understand the effects that we're having on our own planet. And without going into politics or whatever, but, our politics are such that there are people out there that just don't believe that we're having an effect on our planet, even though some of the work that you do makes it obvious. So the question I have is, how do we get the word out to more people so that more people have a better understanding? And this program and the World Science Festival in general is a big part of helping that. But do you have any other ideas of how we can get the word out more so that people really do understand and want to promote policies that help us from damaging our own planet?
Yeah, so at NASA, what we endeavor to do is stay out of the policy discussions and collect and share credible data and have credible models of how the Earth behaves as an integrated system, so that we are we try to stay above the fray, kind of literally and virtually, because we make the observations, we make them as in an impartial, unbiased, rigorous manner, so that the information we bring down from space can be trusted by the public. We publish papers in refereed scientific journals so that our results are evaluated by the scientific community before they're published, and then we leave it to the policymakers to decide what to do with that information. And so by attempting to be unbiased and outside of policy, we hope that our observations can then be trusted and can serve as information on which to base informed decisions into the future. And I think that's the best approach for us as a federal government agency to take in these deliberations about climate change and what their impacts are going to be and what the policy should be around that information. We do a lot of public outreach. We're here, and to try to tell people what we're observing and why we believe those observations are occurring. So thank you for coming to listen about it. It's appreciated.
Yeah. Maybe we have time for perhaps one more question.
Given all these risk considerations, how far longer can the Voyager go?
Anyone hazard a guess?
I think it's a matter of power. They have the power generator, which is RTGs. They have a certain lifetime. And once the amount of power generated by these devices goes down, that's a limiting factor.
Yeah, and actually, the RTGs have performed a lot better than we ever expected them to. So Voyager, in a sense, is a little bit of a science experiment for us. I mean, it's great for an engineer because we have data over that long, but we're actually learning as this mission goes on at how fast or how slowly things degrade. So that power source is actually degrading not quite as fast as we expected it to, and that's why we can still hear from it. And there'll also be the issue of probably one day we'll hit the point also where Voyager might still be healthy, but we won't be able to hear from it anymore because it'll be so far away. But remember that it'll keep continuing going at that speed forever, right? And I don't know if you're familiar with Voyager, but one of my favorite part of the Voyager spacecraft is the golden record that's on there. And that's sort of part of its mission too. I'll say that Voyager's mission is never going to be complete until someone else finds it. It has this golden record that Carl Sagan put on there. Carl Sagan is one of the reasons why I'm where I am today, right? He's an amazing human being, but there's a golden record on that has the sounds of Earth. It has directions on how to find us. So Voyager also has a broader mission. Even when we don't hear from it anymore, I think all of us will know that it's out there representing humanity to the rest of the universe. Yeah.
And I think that's a beautiful point to stop on. So I just briefly to thank all of you for coming here this afternoon to this program. That's big thanks from everybody at the World Science Festival, and your patronage is greatly appreciated. And we hope to see you next year when Voyager will have got a little bit further towards the nearest star. So let's thank our panelists once more.